So in this means test, in this specific section, chapter 10, as opposed to chapter 9, well, I guess that's about as dim as it's going to get. What we're going to do is we're going to compare two means. And so you're going to have a mu sub 1 and a mu sub 2, right? And then you're going to say, okay, are these two numbers the same or are they different? All right. And so before we just had one mu or one x bar that we were evaluating. So now what you're going to ask yourself is, okay, if you have this approach or this mean and you have this mean, which is higher or which is better? And so what you're going to do is you're going to ask the question, does mu sub 1 equal mu sub 2? It's a variation, but this really goes to the heart of comparison testing or means testing. T-testing is mu sub 1 equals mu sub 2, okay? And when mu sub 1 equals mu sub 2, you do not reject the null hypothesis. When they're not equal, you reject. All right? And so how do you know if two numbers are not equal? If you subtract mu sub 2 minus mu sub 1 and it equals 0, are those numbers the same or are they different? This is not a trick question, by the way. They're the same, right? Now, if you subtract them out and you get do not equal to 0, yeah, that means they're not equal. And that's essentially what we're going to do, except we're going to do this for sampling. This is the mu for the population, okay? But we're going to do this for sampling, and that's where we have to take into account what is your p-value, what is your significance level that you're running the test. 2, what is your sample size, and also take into account standard deviation, okay? And once again, we're going to have this discussion of two-tail versus one-tail. Two-tail is if you don't really sense a direction, okay? Because sometimes you'll see this greater than or equal to, so you'll get some direction in there. But what you're going to see is that everything's going to move toward equals to or doesn't equal, or is there a difference, okay? And then the other thing you're going to be deciding on is really on as we go forward is between these two samples, do you also get some type of variance? And that'll be in the next section. And then that's a whole nother discussion as far as whether or not two proportions, and that'll get heavy into proportions, are equal or not. So let's go into this means test. Any questions before we get started on where we're going? And then we'll spend 2 days on this. We'll spend a day on variance. And then we'll spend a day on chi-squared, probably about a half a day on chi-squared. And then what I want to do before we go into the Thanksgiving break, that Tuesday before, we'll have a lab. And essentially what you'll be able to do is I'm going to try and hopefully carve out some time so that you can work on your cases and actually run, create the runs for the t-test and really you're looking at the p-value sort of analysis there. Run those in the lab, and I'll be available to help you out. Okay, that's what we're going to be doing the following, not next Tuesday, but the Tuesday after that. And then you just come back, and you'll see 9 different problems. I think that was one of the requests that came out from the midterm suggestion box, so to speak, is to have more problems. So we'll go through 9 problems, and we'll have 9 presentations from each group, or 1 presentation from 9 groups. Right. Unless somebody wants to do 9 presentations for everybody. Anybody want to do that? No. All right. All right, let me get this thing squared up here. Okay. So what we're going to do is, as it says, we're going to do an inference discussion. What can we infer about this difference between two means as to whether they're equal or not equal? And we're going to start out with sigma known, okay? If we know that sigma, if sigma is known, do you use a z-test or a t-test? Z, exactly. And that's what we're going to start out with. Hey, Josh. That's what we're going to start out with. And then we're going to go into what if the standard deviation of the population is not known. You do a t-test. But one of the big differences here is they're very much the same as what we've talked about before. However, you're going to have to create a pooled sample size. And I'll show you how to do that because it's a kind of a special situation within the comparing two means when you have the standard deviation of the population is not known, because you're more dependent upon the sample size, and that's what drives the t-table. Do sigma unknown, and then here's another specialized situation where we have matched samples. I've put that concept is sometimes a little hard to understand, so I put a short video up on Blackboard relative to matched samples, if you want to take a look at that when at your leisure. So those will be the three things or three areas we'll take a look at, and the population means matched sample will use a standard deviation of the population unknown. I'm pretty sure is what the example is. All right. So here we have this interval estimation, the interval between mu sub 1 and mu sub 2, and so we're going to create hypothesis tests about or around this mu sub 1 minus mu sub 2. And as I said, if mu sub 1 minus, or as we talked about, if mu sub 1 minus mu sub 2 is equal to 0, if you subtract those two out and they're equal to 0, they are the same. If you subtract them out and you get a number other than 0, they're different. So that's the premise of a comparison or the testing between two means. All right, let me see anything here. I think I already covered most of this. So, oh, and then you'll have a simple random sample. So and the first part of what we're going to talk about is where the sample sizes are different. And then after that, we'll talk about where the sample sizes are the same. And in fact, they're so much the same that you're looking at the exact same outcome or this exact same variable. And we'll talk about that a little bit later. It's about, yeah, let's not get too far into this. And, by the way, we're going to push into point estimators. As we've talked about before, there's nothing different here. Ladies and gentlemen, there's nothing different here. We're going to have point estimators for those situations where you don't know the mean of the population. You may not necessarily know the standard deviation of the population. And so then you want to create this point estimator based upon a sample, because as we've talked about before, there's no reason, if you want to test all the vehicles to see what their safety rating is, or you want to find out what 1.2 billion Chinese think about a certain situation, all you have to do is take a certain sample. And as a result of that sample, you create a point estimate, and then you have a certain amount of confidence level or a confidence interval that's created. And we talked about that plus or minus 3% as far as election polls and things like that goes, to determine whether or not is it worth pushing ahead and talking to all 1.2 billion Chinese. The answer is probably no. 1,000 will do it. And just like we had before, you have this expected value. The expected value of your point estimates is equal to the expected value of your population estimates. That's the premise or the underpinnings of sampling. And then you run and then you create that minimum standard, the minimum amount of error that you'll accept in your decision. And that's where we talked about type 1 and type 2 error. All right. When you use an alpha equals 0.05 or p.05, you are accepting the fact that you are going to be right 95% of the time, but you're also going to accept the situation at least as you're making your business decision, that what you found might actually be wrong. We'll talk about it. There's an interval estimate, just as before, where we talk about alpha. 1 minus alpha is beta, okay? Or that's the amount of type 2 error that you pick up. And this is kind of a nuance of comparison of the means when you don't have matched samples. Is you have to create a more or less a blended or a pooled sort of standard deviation or error. And that's what's going on here. For this class and in this text, we don't rely so much on this equation as much as we rely on a pooled sample size. Let's take an example. This is I think does one of the teams have Par Inc. as their case? Anybody looked at that yet? I think Par Inc. I'm not gonna. I'm sorry. Team 4. Who's on Team 4? Do we know? Who's on Team 4? Nobody knows. Oh, well. Who's? You guys are on Team 4? Yes. Yeah. All right. So this'll tee you up, no pun intended, on Par Inc. It's a golf equipment manufacturer. Actually, that was a pun that was intended. I practiced that all morning. Okay. So what you have here is you have this golf ball that was designed for extra distance, and it was designed and manufactured to go a longer distance, because in golf, which is better? This is one of these Geico. Is it a Geico commercial? Which is better, longer distance or shorter distance when you're driving a golf ball? Yeah. Well said, Mitch. Yeah. If you're accurate, it's better to have longer distance, of course. And so you've created this new golf ball, and you're going to sample to see how far this new ball goes relative to the previous ball. And you're going to create a sample of the new ball and the old ball. So here's the data set that we have created. And we've done a crosstab here already for you. So here's the sample size. This is the sample 1 and sample 2. This one went 275 yards, and this one went 258 yards. This was the older ball, by the way. I'm pretty certain. And you know that the standard deviation was 15 and 20. And so what they did was they took this mechanical driving machine, just to make sure there was consistency in the testing, and they drove the exact same way with the exact same piece of equipment. In this case, 120 times on sample 1 and 80 times on sample 2. Yes, that would be. In fact, Casey, that raises a great point. Yes, that would be an external variable or an intervening variable that could affect this testing, and that is a source of invalidity, right? Because if the wind is blowing at your back, that ball is going to go further, and if the wind stops blowing, the ball isn't going to go further. It's just the way things work. All right. So you would actually create this. You might even do this in a wind tunnel potentially, where there is some wind and when there's not some wind. That may be part of your testing methodology. We're going to put together a 95% confidence interval. And here's how we do it. This should look familiar. Is the inference or the point estimators for mu sub 1 and mu sub 2. And the point estimators are x bar 1 and x bar 2, just as we've done before. And then you have this point estimate. x bar sub 1 minus x bar sub 2 as a point estimate for mu sub 1 minus mu sub 2, and you're saying that you're estimating that mu sub 1 minus mu sub 2 is going to be the same as x bar sub 1 minus x bar sub 2. Hello, Jessica. So this is your point estimate. We had the x bar sub 1, x bar sub 2. This is very, very simple. We've done this, hundreds of times, not 100 times, but a lot of times so far. And so we're saying that the point estimate for the difference between the population, if you didn't do a sampling, if you hit this ball 10, because actually you could never, it's an infinite sort of population, because you could hit the ball an infinite number of times. So in this situation, we're accepting that you have to accept some premise that you're going to have to take a sample. You might as well pick a sample that makes sense. In this case, we did 120 and 80. Gazoon tight. Now, this should also look familiar. We are going to create a hypothesis test. And the hypothesis basically says that H sub O it's greater than or equal to, if you get some direction, you get a one-tail analysis. However, the two-tail analysis over here is where you're saying that the difference between these two is equal to d sub 0. And d sub 0 generally, when we're trying to figure out difference, is going to be actually 0. I think should stay so. And the way you create this test statistic is by this formula. And so this is the critical. We're going to first do a critical value approach. As we've done before, we're going to set up our standard distribution. And I'm just going to draw the line here and then the distribution. And then if it's a two-tail, you split the alpha in half. If it's a one-tail, you load it up on whichever side you're testing. And we're going to claim that the center point that used to be just mu, is actually going to be, we're going to call that d sub 0. That's what we're doing here. Everybody see that? Let's take our par inc again. Can we conclude at a p.01, a 99% confidence level, a 99% level that we think we're correct, but there's always this 1% chance that we're wrong, that the balls are greater than the mean driving distance of the golf balls previously, or the two different samples that we're setting up here. And we're going to do the let's just set this up first. So if HO, you have mu sub 1 minus mu sub 2, it's less than or equal to 0, or mu sub 1 minus mu 2 is greater than 0, are we doing a one-tail or two-tail analysis? Why? That's exactly right. So you're going to be loading this up on one side of the distribution, the full 0.01, instead of cutting it in half. You specify your p.01, and there's a 99% confidence level. And see which one we do. I always forget which one we're going to do the critical value first. Remember that 5-step process, the handout from the other day? We're going to calculate the value of z, and here's how we did that. And we got 6.49 when you ran all that out. So that is your t statistic. And so here's the p-value. So at 6.49, if you went to your t table, and look that up, you would get a value less than .0001. And one of the ways you knew that, most important way you knew that, is your critical value at .01. What did we say it was the other day, Casey? It was 2.23. Yeah, 2.2. So what we said was 6.49. This is our reject. This is do not reject. And what we said was, the way we knew this was way off the chart. How do we know it was way off the chart? Way over here. That's exactly right. That t-value is 6.49, and your standard at p.01 was here, and so it's way, way out here. So you've got a very strong indication that there's something going on. There's something happening. And therefore, you would reject the null. You would reject the null hypothesis that they are equal, and you would come back and you would accept that they're different. Questions? .33. There we go. At p.01, we were almost right on our memory. 2.33. Once again, this 6.49, it's very, very different. It's much different than 2.33. In fact, it's much, much higher. So you would therefore reject the null hypothesis because of the critical value approach. So here's an example I want you to work on. And this is you're going to need your Z charts here. You're going to use a Z because we should know the standard deviation. Yeah, we know the population standard deviation. And you're going to see if it's longer than, so once you see the word longer, you go on one tail or two tail. Yeah. So you're going to do a one tail analysis. You know it's Z because you know the standard deviation of the population. And then you know all these, and essentially what you're trying to do is you have this checkout, the scanning lines. I mean, anybody ever in the grocery store and use the scanner? I'm sure everybody has it. Every time, yeah. Sometimes it's just, sometimes I just don't want to do it. And I just walk up and you go, I don't feel like it today, and you go wait in line and catch up on, the latest gossip in Hollywood or something. Yeah, because. Yeah, right. Exactly. That's why you pick a long line, because that way you can read the magazines and you don't have to buy them, right? Yeah. So let me pause this up and go ahead and work on this problem. Now what you have is you have the standard deviation of the population is not known. This is what's going to, hold on. The standard deviation of the population is unknown. That's why it's blank. And now, hey, it stayed up. Everything's working today. It must be, what's today, Thursday? Yeah, all right. So what we're going to do here, this is where the standard deviation of the population is not known. So you're going to have to create some blending in there in order to use your t-table, because because the t-table is going to be more dependent upon the value of n, or your sample size. And generally, unless they're matched pairs, which is a specific situation we'll cover later, you are going to have to use a this discussion as far as blending the two sample sizes. And it's not unusual at all for sample sizes to be different. It's just not. For example, in my research, the sample. Oh, here we go. I'm testing to see whether two states, if you have a control state and a treatment state, as far as this tax credit goes, I'm trying to determine whether or not there is a difference if you, in the employment level, if you introduce this tax credit to people who invest in businesses. It's very similar to an R&D tax credit. And I'm testing to see if they're the same or are they different. Now, is the sample size the exact same in my control group state as it is for my treatment state, Nebraska versus Kansas? No, they're very different. There's different sample sizes that are going on each one. As we did before, you're going to replace in the critical value, if you're doing a two-tail, you're going to replace z sub alpha over 2 with t sub alpha over 2, and you're going to run the t table instead of the z table. And this is what your interval estimate looks like. This is what's sometimes referred to as a pooled standard deviation or pooled error. But keep in mind, if you have two samples and they're not matched and they're not the same, that's why this formula is here, is you have to blend those two sample sizes together to create this degrees of freedom so you can run the chart. And so in essence, you're creating, or in the final analysis, you're creating a blended degrees of freedom. Because if you have one, for example, over in the example we had before, we had n was equal to 50, and then n was equal to 100. What's the degrees of freedom for this test? Is it? I'm sorry? No, the sample size is n on one of them. Sample size sample size on one of them is 100. Sample size on the other is 50.
So it'd be 101 and 51.
But when you're doing the testing, which number do you pick, 51 or 101? See the dilemma? Yeah. You don't know. That's what's going on here. You're blending these degrees of freedom together. Or pooling, as they called it in the textbook. And if you pick 101 or 100 and use the degrees of freedom associated with 99, or degrees of freedom of 99, and you take 50 and you use 49, and then you add them up and divide by 2, might get you close, it might not. Because a lot of it is dependent upon, as you can see in the formula here, it's dependent upon what is the standard deviation for that sample itself. So you can't go right at it. You have to come in at a different angle or a different formula. Now the good news here is that when you get to the software, these sort of calculations are done for you. Let's take an example. Company in Detroit, Specific Motors, General Motors or something, I guess. And they have 24 M cars and 28 J cars, and they want to compare miles per gallon. And here are the numbers that were generated. So what you have here now is you have the 28 J cars, 28 M cars, and you're comparing these two to see, are the miles per gallon the same or different? The uneducated, or the uninformed, what would the uninformed, if they hadn't had this statistics class, go? What would be the conclusion here? I'm sorry? Which would you would say M cars has the better miles per gallon? But wait a minute, this isn't the overall population. This is why this is the, as we've talked before, the underpinning of all things statistics. So now, if you run these numbers based upon a sample at a confidence level, you will be able to determine if there really is a difference between these two samples. How do we do that? we're going to develop a 90% confidence interval. We're going to use these point estimates. And we know that mu sub 1 minus mu sub 2 is equal to 2.5. Now and what they're saying here is that it is possible, based upon sampling, that even though this number looks to be different, 2.5 looks to be different, it may actually be the same. And that's what you want to test. And here's how you get those degrees of freedom. You run through that formula in the, who's got the degrees of freedom? Who's got that? Degrees of freedom. This is on page 471 in your textbook, key formulas. And we ran it through. Okay. And this is going to be a two-tail analysis, by the way. And that's what you get. And it's just a plug and chug at this point. Here again, the computer will do this for you, but it's kind of important that you know what the computer is doing, because the computer is, once again, blending or pooling the degrees of freedom for the two samples that you have going on here, which are very different samples. I mean, one came in, the standard deviation was 2.56, and the other was 1.81. Very, very different. The sample sizes were somewhat different. And here's how you, and this is the confidence level that you've created at P dot, this was at 90% confidence interval. So what they're admitting here is that at this confidence level, there's a 10% chance you're wrong. I think they use P dot 10 probably. Yeah, they use P dot 10. So and what you can say once you've come up with this confidence interval is that you're 90% confident that the difference between these two cars is going to be 1.431 and 3.569. Interesting stuff, for sure. And you can almost begin making a decision here that there is going to be a difference. But let's run this out. Same way as you've done before. And this time you're going to use this test statistic. And you're going to take this test statistic and you're going to create your model. And your model, if you're doing a two-tail analysis, if you're just trying to figure out are they the same or are they different, coming up here, and let's say you're doing a two-tail, you draw your distribution curve as normal, you split the probability in half, and you call this the do not reject, meaning they are the same, and this is the reject, meaning they are not the same. And then you're going to take your test statistic that you're going to create a blended or pooled test statistic. Here, you can't go right at this test statistic because what is it? Is it test statistic? Is it mu sub 1 or mu sub 2, or x bar sub 1 or x bar sub 2? You don't know. You don't know what it exactly is, and that's the purpose of this formula. And then you take your test statistic and you run it against these critical values that you set up at P.05, and if you divide those by 2, it'd be 1.667 or whatever that number is. And then you'd come in here and you'd say if it was in between here. If your test statistic, your t-value came in between your two critical values, you do not reject HO. And if you do not reject HO, what have you concluded? That they are the same. And so here's an example. We're going to take this we're going to run it one more time. Let's see if you, by the way, let's see if you find the typo in here. So let's just say Thursday. Okay. There's a typo in this discussion. No, not, yes. And so here's what you're developing here, is you're saying mu sub 1 minus u sub 2 is less than or equal to 0. And this is a one, so what are you at, a one tail or two tail here? One tail, right. And what are you going to run here if your standard deviation of the population is unknown? You're going to run a t-chart, a t-test. Can't do z, and you can't do two tail because you're at a one tail and you're at a t because you don't know the standard deviation of the population, and you get a sense of direction. We're going to specify this specific value of alpha. Alpha is the probability that you're wrong, that you found something but you're wrong. P.05, alpha is equal to 0.05, a type 1 error. And so you run it out and you create this test statistic at 4.003. This formula looks almost the same as what you had before on your z. And in fact, it looks exactly the same, except you've moved it from, instead of over here you had z, now you have t. That's why the difference between a z and a t is almost not really that big of a deal for the most part as far as understanding the concept. And let's run the p-value approach. And if you ran that out, if you ran all these numbers, you would get a t-value is 4.003, and at 0.005, right, the p-value is less than 0.005. So what would you do at that point? Accept or reject? Yeah. Something's happening. And you kind of started seeing that in the confidence interval, because if you see the confidence interval doesn't go to 0, you're going, oh, okay, well, if the confidence interval never goes to 0, then as far as the difference is concerned, then more than likely there is going to be a difference. Okay. And you actually conclude, kind of coming out of the big picture, or to the big picture, is you now have concluded that at a p.05, at a 95% confidence level, that the miles per gallon difference that you've discovered is indeed statistically significant. Therefore, you would declare that the performance of M cars is greater miles per gallon than the J cars. And so now you're the consumer. Let's take it one step further. You're the consumer, and your primary reason you buy a car or not buy a car, regardless, taking everything aside, is miles per gallon. That's all you care about. What's your decision? Yeah, you're going to go M car. If the only thing that you're making your decision, now, very similar to what Casey mentioned before, there's other variables that come into play. As we talked about with the golfing, there's the wind is going to be a factor. And here, what would be a factor when you're buying a car other than just miles per gallon? Price. What would be another factor when you're buying a car? Speed, how fast it goes. What would be another factor? Maintenance. Oh, that's a good one, yeah. And so you'd have all these variables, and people, like I said, people are they don't know they're doing this, but they're putting $30,000, they're going to spend $30,000, $20,000, $10,000, whatever the number is on a car, and they're betting that that's going to be the car for them. And and in their gut, they say, oh, wait a minute, I'm going to take only a certain amount of risk. And so I say, I'm going to take a risk that I'm 5% wrong, and I'm going to buy this car. Or not buy this car. Let's do the critical value approach. And here, they actually set this up. If t is greater than 1.683, you're going to reject. And you take your, what do we want to do? What do we want to do? Oh, here's a pen. You've got your test statistic, right? And you calculated that it's going to be 1.683 based upon the blended, kind of a blended test statistic. You run it against this module, or against this model, and you come out here at 4.003. How confident are you, using a critical value approach, how confident are you that there is a difference in miles per gallon? Yeah, you're off the chart. You're once again off the chart. A 4, this means basically if you're at a 4, you're 4 standard deviations out. And as we've talked about before, if you're 3 standard deviations out, you've basically included all the potential outcomes. A 4 is off the chart. You are absolutely positively confident that the only reason you're making this, if your sole criteria is miles per gallon, this is the car you want. And you're 99.999% confident that your decision is correct. However, is there a chance you're wrong?
Yes.
What's the chance that you're wrong? Yeah. And that's, what is that called in the